Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 3 on exponential and logarithmic functions. And today we're going to talk about some more properties of logarithms. Logarithms are very useful in calculus for not only because they model real-life situations, but they can be used to sort of algebraically manipulate some expressions and make them a lot easier to work with. And so the tools that you use to do that are called the product rule, the quotient rule, and the power rule. So we're going to be looking at those rules. And then we will use those rules to expand and condense logarithmic expressions. And we'll end this section by talking about the change of base property, which allows you to use your calculator to evaluate logarithms with bases other than 10 and e, which as we mentioned in the last section, are the only two that are built into the calculator. All right, so the first property, which is the product rule, looks like this. If b, m, and n are positive real numbers and b does not equal 1, then log base b of m times n is equal to log base b of m plus log base b of n. This is a kind of strange looking property, even when you have it filled in with actual numbers. And it might be easiest to remember this property in words. It says the logarithm of a product is the sum of the logarithms. So I always like to take a minute or two to explain why that is. And so I put this together. So suppose that log base b of m was 3 and log base b of n was 5. So what I'm going to do with those equations is rewrite them in exponential form. Remember how that works? What is the base? The base is b. What is a logarithm? A logarithm is an exponent, and this logarithm is 3, which means the exponent is 3. That means that b to the third equals m, and similarly b to the fifth equals n. So now I'm going to look at m times n. M times n is b to the third times b to the fifth. Now this is the step that really explains the product rule. When you multiply b to the third times b to the fifth, you get b to the power 3 plus 5. Remember, that's the exponential rule for that. Which of course is b to the 8th. So because m times n is b to the 8th, if we write that back in logarithmic form, it's going to say log base b of m times n equals 8. Where did the 8 come from? It came from 3 plus 5, and 3 is log base b of m, and 5 is log base b of n. So it really comes from the product rule for exponents, is really why this works the way it does. Okay, so here are a couple of examples. We're going to use the product rule to expand each logarithmic expression, starting with log base 6 of 7 times 11, and then log of 100x. So again, these answers are going to come up both at the same time. So first, this one's very simple. Log base 6 of 7 times 11 will just be log base 6 of 7 plus log base 6 of 11. Now there's a little more I can do with this one. Remember that log by itself, not by itself, but with no subscript, is log base 10. So first, using the product rule, we have log of 100x equals log of 100 plus log x. And then, because this is a common logarithm, this is log base 10 of 100. This is asking 10 to what power equals 100? The answer is 2. So the simplest form for log of 100x is 2 plus log x. All right, next we have the quotient rule. And I think the way to really convince you of the quotient rule is to go back to the product rule. Notice it says the logarithm of a product is the sum of the logarithm. So if I asked you to guess what is the logarithm of a quotient, I bet you would guess it's the difference of the logarithms. And that's exactly what it is. The logarithm of a quotient is the difference of the logarithms. In other words, log base b of m over n is equal to log base b of m minus log base b of n. All right, so here are a couple of examples using that. We have log base 8 of 23 over x. Very simple, that's just going to be log base 8 of 23 minus log base 8 of x. And then this is natural log, remember that's log base e. So first using the quotient rule, that's going to become natural log of e to the 5th minus natural log of 11. Now we talked very briefly about this property in the last section. So in general, log base b of b to the x is x. And specifically for natural logarithm, that means the natural log of e to the x is just x. So natural log of e to the 5th is just 5. The simplest form for natural log of e to the 5th over 11 is 5 minus natural log of 11. That brings us to the power rule. The power rule is my favorite rule in this section. I even have a sound effect that goes along with it. And it goes like this. If b and m are positive real numbers with b not equal to 1, and p, as in power, is any real number, then log base b of m to the p equals p times log base b of m. So let me show you how I do my sound effect. And by the way, this is probably the one we use the most in calculus. The power rule says to take this exponent and go plunk it right down in front of the logarithm. Okay. All right. I don't know that this English version is very helpful, so maybe we'll just skip that. All right, so using the power rule to expand each of these expressions. First we have log base 6 of 3 to the 9th. So let me pull up my sound effect here. Log base 6 of 3 to the 9th is take that 9 and put it out front of the logarithm. Next we have natural log of cube root of x. So the first thing you have to do is write that cube root as an exponent. Cube root is 1/3 power. And then you take that exponent and you go put it out front of the natural logarithm. So that simplifies to 1/3 natural log x. And then finally log of x plus 4 squared. You just take the exponent and go out in front of the logarithm. Notice that I am not doing anything with log of x plus 4. There is no rule for simplifying the logarithm of a sum, unfortunately. So you would just leave that as 2 log x plus 4. Sometimes students are tempted to take this log and distribute it, go log x plus log 4. That's not the way it works. Log is a function. It's not something to be distributed. Okay, so just leave it as log of x plus 4. All right, so here's a summary of all of those rules. You have the product rule, the quotient rule, and the power rule. Okay, so this is actually one of the things that we use logarithms for in calculus, and that is to expand logarithmic expressions. So here we have log base b of x to the 4th times the cube root of y. So let's see how that looks. Okay, first thing we're going to do is take cube root of y and rewrite it as y to the 1/3. And now we're going to use our product rule, which says that the log of this times this is equal to log of this plus log of that. And then, this is my favorite part, we're going to use our power rule and go put those exponents out in front of the logarithms. Okay, so when you do a problem like this, in the end, the only logarithms that you should be log of x and log of y, mostly. Okay, there are a couple of exceptions, but you should not have any exponents on the variables inside logarithm, and you shouldn't have any multiplication or division happening inside the logarithm. All right. Now, here's another example. You might want to pause the video and try this one. Okay, this one is a little more complicated. It has a few more steps involved. Okay, so hopefully you paused the video and tried that. Let's compare notes. Eek. Okay, so first, write square root of x as x to the 1/2. Now I'm going to use my quotient rule to write log of this over that equals log this minus log that. Okay, now I still have a product over here, so I'm going to use the product rule to expand this logarithm right here. So notice that they did, well, put it this way. They did a couple of things at the same time. Suppose we left this as a 25 for now. So hopefully you can see that this logarithm right here turned into what's in the parentheses here. So that's just using the product rule. And now the reason that they're writing 25 as 5 squared is because they are getting ready to go and turn this log base 5 of 5 squared into 2 log base 5 of 5. All right, so we have 1/2 log base 5 of x minus the quantity 2 log 5 of 5 plus 3 log 5 of y. Distribute the minus sign, and you get 1/2 log base 5 of x minus 2 log base 5 of 5 minus 3 log base 5 of y. And then the only thing that happened going from here to here is they're using the fact that log base 5 of 5 equals 1. That was a special property early in 3.2. Said that log base b of b is always 1. So in particular, log base 5 of 5 is 1. So the simplest form, sorry, I lost my mouse, for this expression, if you completely expand it as much as you can, is 1/2 log base 5 of x minus 2 minus 3 log base 5 of y. Okay, now you can also go in the other direction. These properties look the same as the ones we looked at a few slides ago. It's just that they've taken the left side and the right side of the equations and switched them around. So they're using these forms of the properties to condense logarithmic expressions, which is the reverse of what we were just doing. So the directions in this kind of problem are going to say write as a single logarithm. And you have these examples here. So we'll start with log 25 plus log 4. Oops. Okay. Well, I'll go back and forth between these two slides. All right. So using the product rule, log 25 plus log 4 equals the log of 25 times 4. And of course, 25 times 4 is 100. And as we've noted a couple times before, log of 100 equals 2. Next, we have log of 7x plus 6 minus log x. We're going to use the quotient rule on that one. And that's simply going to be log of 7x plus 6 over x. All right, now when I'm condensing a logarithmic expression, I have a different version of my sound effect. So what I'm going to do in letter C is I'm going to start by taking this 2 and going and putting it up here and making it the exponent, and I'm going to do the same thing with the 1/3. Make that the exponent. So now, oops, let's get rid of these. So now we have natural log x squared plus natural log x plus 5 to the 1/3. I'm going to use the product rule to condense those. Natural log this plus natural log that equals the natural log of this times that. And then finally, this step is probably not strictly required, but they're writing the 1/3 power as cube root. So the condensed form of this logarithm is natural log of x squared times the cube root of x plus 5. And that brings us to the change of base property. And you know what? I think I'm going to skip right over this version because this is talking in general about any base A. We really only use this with base 10 and base E. So suppose I ask you, what is log base 5 of 37? All right. You don't have a log base 5 button on your calculator. But what this is saying you can do is you actually can do one of two things. If it was log base 5 of 37, you could ask your calculator what is log 37 minus log 5. Or if you like natural log better, you could ask what is natural log 37 divided by natural log 5. So it's kind of interesting that those always come out to the same thing. And I will convince you here in a second that they come out to the same thing by looking at this example. So if we wanted to evaluate log base 7 of 2,506, first of all, let's get an idea for, kind of what ballpark that answer should be in. So this is asking what power of 7 is 2,506? Well, 7 to the second is 49. 7 to the third is 343. And I think 7 to the fourth is 2,401. So the answer should be a little more than 4. So if we use common logarithms, and I think I will switch over to my calculator. I'll do it at the end. Let's see. Good, I still have it open. You can do common log of 2,506 divided by log 7, and that comes out to approximately 4.02. So it is a little more than 4. If you use natural logarithms, it would just be natural log 2,506 divided by natural log 7. So let's look at the calculator here real quick. You have to be kind of careful how you enter this one. All right, so if I'm using common log, I would do log 2,506. Oops. Make sure you close the parentheses and divide by log 7. So 4.02199. If we were rounding to 2 decimal places, that would be 4.02. If I do it with natural log, I'm supposed to get the same answer. Exactly the same answer. So it doesn't matter if you use common log or natural log. You will get the same answer. And I believe that's it for section 3.3. We will see you next time.